Hi everyone. So let us very quickly review the sampling distribution, and then we will start with estimation. Um, just to remind you that the new assignment 2 has been uploaded. So the deadline is by the end of this month. Okay. So very quickly, we are now reviewing the sampling distribution, and then because this is the thing we need for the today's estimation. Okay. But before we start, any question? Any question before we start? Um, if no, then let's get started. Very quickly, we just review the previous chapter, sampling distribution. So with input random sample, and we learned the sample mean is the mean or the expectation of the sample observations. And we know one thing is the expectation of sample mean is same as population mean, and the variance sample mean will be the population variance of n. Okay, that is the error. And the important thing is we know the sample mean is same as the population mean, right? The mean sample mean, population mean, and variance sample variance is population variance of n. And central limit theorem tells us when n is large, then this is normal, approximately normal. Okay, it's close to normal. It's not exactly normal, but what it said is any large enough, then it's close as normal as we want to. And this is good, but there are two things: is we don't know where's mu, what is sigma. Okay, that's a little bit issue here. But assume we know it, then that's not an issue. Okay, and um, and then we learn a special case of sample proportion, where x are either 0 or 1, and then we have some special formula, okay? Because in that case, the variance, the mean is the sample proportion, uh, and the sample variance is related to pi only, right? So basically, it's uh, the expected value of x bar, which is pi, p is pi, okay? So in that case, the central limit theorem tell us this much simpler formula, okay? And and then what we cover last class is the last thing is when sigma, the population variance is not known, okay? So we will replace it by s squared with the sample variance, right? Which is n minus 1, okay? And replace this, okay? What would be that distribution is, okay? Turn out we save the proof. This is the t distribution, okay? With d equal to n minus 1, okay? So now it's, roughly speaking, you know why we have t. We use the sample variance is t is using n minus 1, okay? That's why one way is this have a nice distribution, okay? Of course, we'll give you further justification in this class. But before we end this, we have two technical slides about how to prove why this is t. Okay, uh, let's get started. Two technical slides. But can you see the screen? Yeah. Okay. So everything now up to now is just a review. So now we just start very quickly to explain why this is t. Okay. So we will state these two properties without proof. So we are not proving it. And these two will be the reason why this is true. Okay. So the first thing is if x and n are random sample from normal, okay, we rely the normal here. We need the normal, okay, and x bar, okay, would be the average of observations, okay, and sample variance, right, will be the minus the mean square over n minus 1, okay? And turn out that this particular quantity, sum of the difference between the mean and square over the sigma square is actually chi-square n minus 1 distribution. Okay, it's not n, but n minus 1. Okay, and the x bar and s star are independent variable. Okay, so which means that they're covariance 0 and so on and so forth. Okay, so these are the two facts. We don't prove it. It's too advanced for class, but this is the two facts. Rely on these two facts, we can prove our result. Okay. Now, first is look at the following. S square over sigma square. Okay. This is S square, right? And we just shown this is chi-square, right? This is the first property. Okay. First property. We didn't prove it, but this is the first result. Okay. And okay. And the second property, these two independent. Okay. Then we already know that this is by central limit theorem or property of normal. This is standardized, will be a standard normal. Okay. So now the trick is here. Okay. So look carefully. This is the trick. So this, okay, is here. Okay. And the trick here is I have this and this. Okay. They cancel out. Okay. You divide both the numerator and denominator by sigma. Okay. And you do notice that this is coming from here. That is z. Okay. And this part, s square over sigma square, okay, is chi-square over n minus 1, which is proven above. Okay. So a normal over chi-square degree from n over n minus 1 is t. Okay. So that's why we have t to the degree n minus 1. Okay. This is how we prove t. Okay. Of course, this is rather technical, but this is something they're trying to show you what is t behind. Okay. I guess that would be something a little bit trickier, but it's not something complicated. But anyway, actually, Eddie, let me know if you have any question. Of course, this is a technical part. It's not expected to be included in the exams, but I hope you would be able to see why they make sense. Is that okay? Any question? Any question? If no, then we will talk about the estimation part. Is there any question? No? So let us get started with the estimation. Okay, so that is the, I think that is the one of the applications we learned from the previous chapter. Okay, so so although we finished one topic, the next class we don't have quiz because I think it would be more useful to have the quiz at the same time with the I think with the next chapter. So I will make the quiz combine the two quiz together. So I think the two quiz are the same. So combine the same one to save time because we are slightly behind the schedule. So with the quiz together with the estimation. So let's get started. So estimation is trying to guess, right? So what are we trying to guess? Okay. So we have can you see the slide? So what are we actually guessing here is we have population here, okay? We want to know something about population. So we denote it as theta. We call value interest, but something interests us. So what's interest us? Maybe we care about the mean, we may care about the median, we may care about maybe variance, right? Maybe care about a lot of other stuff, okay? There's some summary statistics we may care about, right? But of course, for the purpose of our class, we are trying to only guess one thing. We only care about the mean, okay? And also the variance, okay? The many things we care, but this is the two things that we care most. Since you know this is the two things actually we learn most of the time. And we try to figure out the way to estimate those, okay? And that is important, right? Because we want to see, say, mean, right? What's the mean income of the population, right? What is the average wages made by some people, or how in application business, right? We want to care about what is the mean consumption in our store and so on and so forth, right? And also we care about the variance, right? As some of you are from finance and accounting, the risk estimation involve variance. So that are the two things that we care most, okay? And how to estimate those, right? The population we can never observe, right? So in the real world, we are going to do it by sampling. That's we learned in last class, right? We learn some sample, okay? And sample, we have some observation, right? We just grab something here, we try to grab from those. And how to, then from the sample, we want to come up way to estimate, say, mean and variance, right? This is called estimator, okay? Estimator, you can imagine a formula, okay? A random variable, okay? Because why the random variable is because depending on what you draw here, right? There's many ways you can draw this from a sample. So this one is a sampling, right? Because the population itself has no uncertainty, right? But depends on what kind of sample you draw, right? You come out with different sample, and before you draw, you don't know what it is, right? Because that's why they're sample, okay? And everything is a random variable here, right? Because you don't know what is you draw in the sample, and based on the sample, okay, you try to estimate, right? What example estimator you have, right, is what we have is sample mean, right? It's just trying to say X bar, right? The X bar is one of the estimator, right? It's S square, right? The sample variance are two estimator, right? You know very well. I mean, actually from the last class, right? And usually it depends on sample size. Okay, that's why I drew by n, right? Because this is, you remember the sum of x minus x bar over n minus 1, right? This is sum of the xi over n, okay? So it depends on n, right? N minus 1 here, okay? So that's depend on n. Sometimes it may not depend on n, but most of the time, yes, right? And what's estimate? Estimate is once you draw the sample, the exactly value is the estimate. So particular realized value. Okay. Estimator is the random variable. Okay. And the two type of estimator we will learn. I don't know if we cover both, but at least we will learn today is the point estimator. Point estimator give us 1 point. So the one we have x bar and s square is a number, right? So this is a point estimator. And the next thing we'll try to do it, I don't know whether I can do it this class or next class, is called interval estimator. Instead of giving a point, okay, you are trying to give them, this is the range of the point that we're trying to guess, instead of guessing one particular point, okay? Say, very often, right, you go to read the financial news, right? The expert said, oh, what is today's, in the morning, then what is today's Hang Seng Index, okay? And he will say, probably say, oh, it's unlikely that he'll say, today's the Hang Seng Index is such a number, okay? Give you particular estimate, right? It's not going to say, oh, 25,000. You know, usually don't like this, right? It will give you a range. The range is the interval estimator, okay? Because by giving you a range, it's more likely to get it right? And also when you look at the investment bank, the analyst report for a particular stock, right? You say, oh, particular stock A, the target price is $50, okay? That's a point estimator. But when we say the price may be 45 to 56, then it's an interval estimator. Okay, it gives you a range of the value to be your guess instead of giving 1 point guess. Okay, so we will give you so this chapter we divided into 2 parts. The first part will be the point estimator. The second part will be interval estimator. Okay, any question before we proceed? Any question? So let me know if you have a question. If you don't have a question, can you type no? Is that okay? Okay. So now, thank you. So now we are going to try to give you the idea of what is a good point estimator, right? Because this is the point estimator we start with. What is good point estimator? Okay. So these are the 3 common good property we want. Okay. The first one probably you already know it is what we call unbiasedness. Okay. Which is a property you know very well is the expected value of the sample mean is the population mean. Okay. So if you want to use the sample mean to estimate population mean, okay, that's a good thing. It means that we roughly hit the target, okay, on average, okay, because it means suppose this is the mu, okay, it means that in a 2-dimensional graph, maybe the first sample mean is here, the second sample mean is here, the other sample mean is here. So the average of these 3 will give you the center, okay? So because this depends on what you drawn from the sample, it means if you drawn this sample, repeat the sample process many times, we get what we want. Okay, so that means that it's like the application of in the US election, right? And there's many people who do the survey or the poll, try to ask whether you support Trump or Biden, right? But there are many polls. They aggregate them, add together. That will give you a correct estimate or a target. Okay, but doesn't mean that it falls in target. It means if hypothetically we repeat this process many times, the average of those will meet the target. Okay, but doesn't mean itself meet the target. Okay, it means, but this is just hypothetical. Okay, but unbiasedness is something that usually we hope to have. Okay, but sometimes it's hard, but it's something we want to have. The second one is consistency. This one will be something I think is easier to understand, although in terms of notation, it's more complicated. The technical definition is when n goes to infinity, which means that if you increase the sample size continuously, but there's no n, keep going, doing a lot, at the end, what you're trying to estimate is exactly what we want. Okay? It means the following. So this is the mu, what we want to estimate. Okay? And this is x bar, okay? And, okay? If you have eventually this guy, I don't know how it goes, but as n increase, it will be going closer and closer and closer and closer and closer. At the end, you reach the mu, okay? So here is you increase n, this is the path, okay? You get closer. You may get closer in very funny way, but maybe in this way, maybe in that way, whatever way, but it can increase and decrease, it can be further, can be anywhere, it doesn't really matter. You can go the other direction, okay? But at the end of the day, what we say is as n goes, you will hit the target, okay? Just like if you try to doing the arrow, right? There's a bullseye, right? Right. So eventually, maybe you hit here, you hit here, you hit closer and closer. At the end, you hit the bullseye. Okay, so that is you hit the target eventually if more and more and more sample is used. Okay, so just this one is repeat sampling. You hit the target on average. This one you exactly hit the target if you increase n. Okay, and consistency is something we hope to have, and this is the most important thing usually, right? At least you need consistent, right? It at least need that at the very end of the day, we have infinite amount of resources, we should get it, okay? If this is not satisfied, then probably there's a problem, okay? And the second, and you can easily see that if unbiased, right, usually is consistent, okay? And sometimes even it's biased, it's still consistent, okay? So consistent is something that is it's not difficult to achieve, so that's why we usually want to have it, okay? The next one is efficiency, okay? If there are two estimated that are unbiased, okay, turn out to be there quite a lot of those, then what you pick the one that's more efficient, okay? Efficient means is the variance is smaller, okay? A is more efficient than B if A is smaller, okay? So what does that mean is, suppose this is the mu, okay? And suppose A is something like this, okay? It's A, okay? They on average, I think it's in the mu, okay? And suppose B is here, okay? This is B, okay? B is further away from the average distance of B from the mu is larger than A, okay? So A is more efficient than B. So it means that it's closer to the target we want. Okay? Is that fine for the free property? Okay, someone asked me what a limit means, okay? So limit is the notation, this limit and infinity. Okay. I use mu. Theta is anything, right? But one of the things you can imagine that we're estimating is the mu, because theta is the variable interest, can be you can imagine it's mu, can be sigma square, can be many things. So that's the second thing here, means this limit, okay? Just to forget about technical term, means when n okay, what it means is, okay, this one will be as close as we want. Okay. So technically defined will be, we need an epsilon delta idea, but what it means, okay, to put it simple, just saying that when n getting closer and closer and closer, this and theta will be very close. So technically, actually means you give me a very small number, no matter how small it is, okay, to define the difference between the two, okay. I can always find a large enough n to satisfy this condition. So limit just mean if you don't do this, you say this is very close to, I don't know where close, but you can, okay, roughly can say this is will become this, or as close as you want, if n is very, very large. Okay. But sometimes it may not exactly there, but just say that no matter how small you want, we can increase the sample size to achieve this difference. Okay, that would be the best explanation. Would be saying that you give me very small number epsilon, okay, and maybe 0.0001, okay. Then I can say no matter how small you want this and this to be, okay, I want the difference between this is such a very small number. I can always find a sample size to improve the precision. So that, which means that no matter how small the difference, the margin of error you want, I can always increase n to make that achievable. I don't know hold in. I don't know either explain close enough to that, but this is very rather complicated idea to explain limit. So Joseph asks, if point estimate a certain value of the population, does it mean you cannot use it? No. It's unrelated to continuous or discrete random variable. Everything can be anything discrete or continuous. So point estimate target certain variable population? No. Point estimator, what point estimator here is, say suppose sample mean is the estimator. Okay, simple mean, right? But you can also use the geometric mean, you can use harmonic mean, or those kind of thing, right? And what is said here is it is applied to both discrete and continuous. I don't know whether I answer your question, Joseph. Doesn't really matter. Maybe it will be more clear if you give example, but let's give example. What are the estimator you have here? Okay. So as we said, usually we're interested in population mean and population variance. Okay. And so we know from the first chapter, these two are the natural starting point, okay? We have promised you to prove why this is true, okay? And this is the definition, right? So we'll prove, okay? These two are unbiased estimator. Okay? And further, we will show you sample mean, okay, is an efficient estimator. Okay? Not only unbiased, it's also efficient. Okay? And I don't think we put in the slide, but this is also a consistent estimator. Okay, but we don't have time to, I don't think we prove it, but this is something that we don't show it, but this is true. Efficient, we will immediately show it. And we'll show, first we'll show, the next slide, we'll show this efficient and then bias. Okay, so that's why sample mean is good. And the next thing is we will show this is unbiased, and that's justify you need n-1. Okay, so that's the goal. Okay, before the break, we want to show you the first two results. The X bar is efficient and unbiased. Okay, and actually unbiasedness we actually show in the last class, right? Because X bar is summation xi over n, right? Any expectation is mu, okay? So X bar will be expected sum of xi over n, okay? You can take one for n out just to recall you. And then you can take summation expectation swap, okay? Because this is the property of the expectation, right? And the n of them, there will be n of mu, okay? Sorry. Maybe summation of mu, okay? But the n of them, so there's n mu, so this is mu. Okay, so that is why we have this one. Okay, but actually you can hold more generally, right? Here actually we don't use n over 1 over n, right? Actually we can use the any weighted mean, as long as the weighted is fine, right? So if you do this, omega xi over sum of omega, okay, and this is the sample, this is weighted mean, right? This weighted mean is also unbiased. Actually, you can repeat the proof. 1 over n becomes sum of the mu, right? Right, this become 1 over sum of the mu, and this is the same is sum of this omega I mu, and they cancel out, is still mu. Okay, so any weighted mean is also mu. Okay, for this point, is it okay? So the question here is simple mean and the weighted mean is also unbiased estimator. Why we use sample mean all the time? Okay, so the question is, we have been using this all the time, right? So why is the case? Why? Okay, so here is the proof. Okay, the proof will be is that because sample mean, the one we do, is better than any other weighted mean. Okay, so weighted mean means, just to recall, is we can simplify saying the weighting, I'll just sum to 1. Okay, the sample mean is just 1 over, every weighting is 1 over n. Okay, but this is generally we can do this without loss or generality, the same thing, okay? All the weighting is just normalized to 1, okay? Now we calculate the variance here. Variance of the weighted mean, okay? Variance of the weighted mean, okay? Because all the xi are independent, okay? Varying the sum is sum of the variance. You can put the variance inside, okay? You can put inside without any problem, okay? So that is the first step, okay? The second step would be using the property of variance ax is a square variance of x, okay? You multiply by constant, then you constant square, okay? So that is the second step here, okay? You take it out, will be square. So that is the step here. And the next step is this is the sigma square, right? This is sigma square, okay? And the next step is we can take the sigma square out, okay? So that's here. So the last step requires to use what we call the Causes Was inequality, okay? So we don't prove it for those who learn, I think, higher math, then you know this, but we just use it, okay? So what it says is, very interesting property is, suppose you have a bunch of numbers, u up to n, and there's another bunch of numbers, v up to n, and what it said is, if you square those number add together, okay, and you square the another set, okay, you multiply their sum, okay, you multiply their sum with bigger than, interestingly, you multiply them each pair by pair, okay, u1 v1, u2 v2, okay, and then until un vn, and then square, okay. So is the first is sum of the squares, okay. The product of sum of square is bigger than sum of the product square, okay. So in this particular case, we take u is mu, v are all ones, okay. So sum of the one square is n here, okay, and this is sum of the mu I square, okay, and this is sum of the mu I square, okay, and this is 1, okay. So that's why what it means here is sum of the mu I square is bigger than 1 over n, okay. So that is what the Causes Was inequality gave us, is sum of the mu I square equal to n, okay. If you don't follow this, just apply the formula. So there's nothing to see here. What it means is sum of the mu I square, the minimum will be achieved by 1 over n, okay. So the minimum is here, which exactly the variance of the sample mean, okay. So that exactly what we want to prove is the sample mean, okay, is the have smallest variance compared to any other weighted average mean, okay. Any question? Okay. If no, then we'll break of 10 minutes because we start a little bit late. So let's resume after 9:32 p.m. Then I'm here to answer any question you might have. Okay, so I think we should resume. Any question before we proceed? So before the break, we proved two things. One is sample mean is unbiased. Okay. Okay. And the variance, the second one is the variance of sample mean is less than smaller than any weighted mean. Okay. For any weighting. Okay. So that is the weighted mean. Okay. So that means that if you want to guess the sample population mean, the sample mean is better than any weighted average. Okay. So that's why this is something we often use. We don't use the simple mean is the best. Okay. So now we're trying to explain this. You keep asking why we have n minus 1 not n. So now we give you the proof. Okay. So I hope it's clear what we're talking. So can you see the screen? Just to make sure. Good. So we're trying to prove why that's the case. Okay. So why this is the case? Okay. Why? Because this is turned out to be an unbiased estimate of this, which said this is the case. Okay. So that is the explanation why we use n minus 1. So that means that if you have something called sigma hat, which is 1 over n summation xi minus x bar, okay, and turn out to be this one is not sigma square, okay. So this is the case why we don't use this one, okay. We use this guy, okay. Now we're giving you the proof. The proof is not very complicated. I'll try to explain step by step because that would be probably the last few proof we're doing in this course, except there's some proof in the regression, but other than that, we don't have much more proof. Okay, so here is the meaning, right? S squared, take n minus 1 out. So just because S squared is 1 over n summation xi minus x bar square. This n is expectation, just put it inside. Okay, so this is the first step. The second step involves writing out the summation. Okay, the summation is this, writing out this guy, right? This a minus b square is a square minus 2ab plus b square. Okay, so that's a, b, 2ab. Okay, and now here is some of this, say first, this is some of the x bar square, okay? And x bar squares didn't depend on any I, so that's why n of them. Okay? And second is you can take the expectation in, right? Summation of them, right? Because actually what we are doing here is x plus y is equal to expected x plus expected y, okay? You put expectation in, okay, is expected to x bar xi, okay, will be equal to negative x bar. You can take it out, it's a constant, expected xi. Expected xi is x bar. So that's why we have x bar square, okay? And because summation, right? So that's why the n, okay? So that's why 2n x bar square, okay? And this xi, okay, expectation of that, okay, is they're the same id, so there's no different from forgetting about the subscript, okay, same as that, okay, and then put it in, okay, you can see the x bar to n minus n, so that's why we have minus n, okay, and n can be taken out, so this will be same as this. So the same n taken out here, common factor, so we n over n minus 1, you have this guy. Is that okay for this one? Okay, so now the key here is to figure out this guy. What's this? Okay. Is that a question? So there's some math here, okay, but not too difficult, okay. Expected square of the mean, okay. Mean itself is summing all the observation divided by n, okay. And this n square can be taken out, right? You square it out, okay. And here what remains is sum of the xi square, okay, which means is x1 plus x2 blah da 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 up to xn square, okay. And how to do that, right? Is you can imagine it's a table form, right? Xn, x1, xn, right? You just add up everything in the table, okay? Then that's fine, right? Because how you square is multiply each element with other element, right? That is called the distribution rule, right? So that is what you can see is the diagonals, okay, are the sum of the square, right? Because x1 times x1, x2 times x2, xn times xn give you this sum of the xi squares, okay? And what is not there will be, they are not sum of the squares, right? And these are color. So all other things not non-diagonal, okay? Other things not in diagonal are here, okay? So this is the diagonal. These are the non-diagonal, okay? And the sum of all the diagonal element will be same as n of this guy, right? Because each are the same ID, right? And what's this? The product of them, right? Expectation, you can put inside the sum, right? This is expectation of xi, xj, okay? And because the independent, okay? So it will be same as this one, okay? So probably I didn't, so this is the important property that I didn't write that down. So will be same as this because they are independent, okay? Independent are equal to the product. So that's why will be expected x squared. And how many of them will be n times n minus 1, okay? The reason is how many terms here is n squared. N squared minus the n, so that's why n times n minus 1. Is that okay? And okay, so what the n can be cancelled out, okay? So that's what you have, 1 over n x squared and n minus 1 expected x squared. Okay, do note that these are not the same. Okay, this is expected x squared. This is expected value of x squared. This is square of the expected x. Okay, now what remain here, the final step, is to show you the expected s squared, right? Which we have shown this guy. Okay, the previous slide is to put this thing, right? 1 over n x squared plus n minus 1 ex squared. Okay, and this, right, is n times n minus 1 expected x squared, and this is n minus 1 over n squared. Okay, and this n and n minus 1 cancel out. Okay, so that's why you left this guy. Okay, that is actually the definition of variance, right? Because variance of x is expected x squared minus expected x squared. Okay, so that is showing this unbiasedness is expected s is sigma squared. Okay, so end up with this final proof. Is that okay? Is there any question? Any question? Is it clear why with n minus 1? Because I promise you to prove it in this topic. So this is being proved. Any question? Or is there any step you want me to go over again? If you have any, if I go over too quick. If okay, can I type okay? Okay, in case you, I don't know if you follow, but hopefully you can follow. But anyway, as we said, this is all the technical proof. So why we have, someone asked me why this, okay, there's some question, I think about, Hanju, is it about the last slide, I guess? Are you asking why this guy? Am I right? Why this is the case? Because, okay, look at this again, okay? Is it okay 1 over n become n squared? Is it fine for this one? Because square, right? And this guy is x1 plus x2 up to xn square. Okay, what it is, okay? So let us give you example what we have. Suppose n is 3, maybe n is 4, okay? x1, x2, x3, x4, right? x1, x2, x3, x4, right? How I multiply them, right? You have x1 square, you have x2 square, you have x3 square, you x4 square. So there are 4 of them. So let's give you this guy. You count the diagonal. Is that okay for this one? Okay. The second one is non-diagonal, right? Will be x1, x2, right? This is x1, x2, okay? x1, x3, so on and so forth, okay? How many of them, right? Total, how many terms of them is 60 terms, right? And diagonal is 4, so 60 minus 4 is 12, or n squared minus n, so that's why n times n minus 1. Is that okay for this one? Okay, and all these terms are not the same guy, right? So the expected value of x xi xj, okay, will be equal to expected xi times xj, okay. Why this is true? Because there's a result, covariance x and y is equal to expected x y minus expected x times expected y, okay. And covariance, if they're independent, covariance is 0, okay. So that's why expected xy is expected x times expected y if they're independent, okay. So the expected value of not the same term will be expected x squared, and the n times n minus 1 of them. Is that okay? Is that okay? Then n comes out and cancel, so that's why you left this guy. Is that okay from this onward? Or you still have question? Okay. Another question is plug the SD formula in page 8. Is that correct? SD formula. Let me see. I think I can erase this slide. The question is, I erase plug SD in the formula here. Are you asking this question, Vicky?
I mean, 我用中文講啦，即係你第10頁咧，你咪計咗嗰個 square 出嚟嘅，跟住然後係咪應該要將嗰個依個數塞翻落去第8頁嗰個 formula 嗰度？
我唔使嘅，呢個就係你呢度就係有呢個 this is the term, right?
係。
So page 8 and page 9 is this guy. You put this back into here.
即係我第10頁計咗佢係等於
sigma square， 咁就做完㗎啦。You are done here because
即係我淨係最後其實就係得到成條 formula 就係等於呢一個 sigma square。
So the key here is I'm trying to show this. Why we want to care about this? Because we want to say the sample variance on expectation is exactly the population variance.
Oh, okay, thank you.
Because if we say why this is important, suppose we care about, we use the same formula for the variance. Okay, suppose we do this. Okay, then what you see is this guy, okay, will be equal to n over n minus 1 sigma square. Let me see. Times n, oh, sorry. So this will be, let me prove it. So this will be expected n over n minus 1 s squared. So that's why it's n over n minus 1 expected n squared will be n over n minus 1 sigma square. Okay, so that means that if you use this formula, it's not equal to this guy. So that is the implication here. Vicky, do you get that?
Yes, thank you.
So that's why we need n minus 1.
Thank you.
Any more questions? Very good question. So any more questions? Just because the goal is to say why with n minus 1. Okay, so if no further question, then we go to a special case, which is proportion. Okay, proportion means the value is either 0 or 1. Okay. In that case, there's nothing to say anymore because the sample average sample mean is a unbiased we have shown, right? Now a special case, but still this everything holds. This is still unbiased, okay? And it's still efficient. Okay. Sorry, efficient. And one thing is the sample variance, okay? Is directly we can use the sample mean 1 minus sample mean over n. Okay, that is a something turned out to be different from we don't have n minus 1 because it's binomial, so that's why this is something that I added special thing here. So this is something to know. Okay, this is a better estimator. Is that okay for this one? Any more question? Okay. If no, then we will go to a part called interval estimator. Okay. This interval estimator is something easy to calculate, and I would say it's very difficult to understand precisely what it is. It's not easy to understand, but hopefully you will be pay attention to understand what it means. Okay. So let's get started. Just a little bit trickier than usual. Okay, the math is rather simple, but just the resulting math in this topic will be easy. Okay, but there will be conceptually something we need to be careful. Okay, so central limit theorem said the sample mean, okay, is approximately this one, right? If you have n is big enough, n is large, okay, we have that in the last topic. Okay, so the question is, when I give a sample, the sample mean is a good estimator, right? We estimate point. Okay, so instead of giving us a point, can we give us a more point, because estimate 1 point usually you're going not to fit it, right? Can we give a more precise statement? Okay. The question is, what we want is to find a symmetric interval about the mean. Okay, and more precisely, we are saying that consider any alpha between 0 and 1. Okay, we want to figure out what is the z. Okay, such that this is between 1 minus alpha and 1 plus alpha, right? Or actually we want to find this guy, right? A and B, okay? Alpha is the weighting. Yeah, alpha is weighting. Any number between 0 and 1. Stand for weights. Just stand for some probability. Maybe you want to say alpha is very small. Usually you want alpha is a small number. You can imagine alpha is, for our purpose, you can imagine alpha is margin of error. We want it as small as possible. Okay. Usually what's alpha, usually value, you'll be very clear later, will be usually 1.5 or 0.1 or 0.01, something small number. The reason why we want this is we want a range of value between A and B, okay, such that the sample mean usually fall between these two values. So we want alpha as small as possible. Is it clear what the alpha is? Alpha is spelled as alpha. Is that okay, Hui? So we want A and B here, but we want symmetric. So basically, just to rewrite it is like X bar minus ME, we call ME marginal error. Later you will see plus ME, something like this, because symmetric about the mean. Okay, but anyway, let's forget about it. You'll be more clear later. But the thing is, now we can we write this because this is a normal. Okay, we can standardize it, right? Minus the mu and this. Remember, this is the variance of sample mean. Okay, so this is standardized normal Z. Okay, this is what we want. Okay. So basically, let's repeat. We want to estimate mu. What we want to do is use X bar. Okay. And for this X bar, we want more. Instead of giving X bar, we are saying that can we have this, okay, to estimate. I estimate this instead of 1 point. I estimate a bunch of points. And how to estimate bunch of point is I say I go give a circle, right, of X bar, give it around it, and try to guess what it is, right? If your number line means the following, right? Instead of giving X bar, I would give X bar minus something M, say X bar plus M. I want to guess this interval, okay? And this is symmetric about this guy. So we want the difference between this and the mean, okay, is closest enough as possible, okay? So of course, on average, this will be 0, right? Because on average, this will become 0, but we want to check this is what we want to say. And what does that mean? We'll become more clear, but let's go to the math first, okay? So that means that if you write, this is Z, right? We want to find the C such that this is 1 minus alpha, okay? And in that case, C is Z alpha. What is Z alpha? Z alpha, which we often use in this class, will be the right tail. The right tail is alpha. So this is a bell curve. This is 0. The area is alpha, is Z alpha, okay? And if this is alpha, this is Z negative, because symmetric about 0, that would be Z alpha negative, okay? Or some, yes, so this is the notation here, okay? And actually, we know how to do it, right? If in Excel, then you will be, what you'll be doing, right? Will be using the norm standard inward alpha, okay? Actually, this is the negative C alpha, right? Because they give you the left tail, okay? So you need to be 1 minus this gives you the 1 minus norm as invert alpha will give you Z alpha, okay? So if you write this and then replace Z by this guy, right? And C now we know this is this guy, okay? And you multiply both sides by sigma over n, right? And then you multiply both sides, sorry, plus both sides you move mu to the other side, two side, okay? So that is something very interesting, turn out to be. We have a statement about mu, okay? Actually, it should be statement about x bar, okay? X bar minus this and x bar plus that, okay? Have probability of this, okay? Is between one minus alpha, okay? We'll be very careful about the probability statement, okay? The probability statement is about the x bar, right? Mu is something, population mean is nothing about probabilistic about that. It's always the probability or the random variable is about the x bar, okay? Saying that if the probability that the x bar plus this, x bar minus this will include mu, okay? With this probability, okay? But the real fact is we don't have, this is not probabilistic, right? We never know it. And this is only probabilistic before you draw this sample. Once you draw the sample, it's no longer probabilistic, okay? So that's why we don't call probability. Sometimes we call confidence, okay? We'll explain a little bit more later, but that will be, we'll explain the next slide, but the next two slides. But what we have is this formula, okay? This formula you need to keep in your mind, okay? This is the formula, the interval estimator, when you try to get the sample mean, okay? The point estimator is x bar, okay? The interval estimator is, okay, instead of asking x bar, I estimate more, okay? How much more you do, okay? You would add something we call z alpha over 2 sigma over root n, okay? And you subtract the same quantity, z alpha over 2 sigma over n, okay? Why alpha over 2? Because both sides alpha over 2, okay? The center one is 1 minus alpha. Is there any question on this one first? Please feel free to ask because that is rather complicated. Yes, this is exactly because symmetric, so that's why alpha over 2. You say because the normal is symmetric, so you assign alpha over 2 on both sides, the center will be 1 minus alpha. Because what we want is there's a 1 minus alpha probability that the sample mean will include the population mean. So we want the probability that include the population mean will be large. Of course, alpha usually is a small number. Okay. It will be more clear in the next slide, and I give example. You'll be more right sigma divided by root n because the normal sample mean is this, and this guy, law of large number, central limit theorem, is this guy. So the standard deviation is sigma over root n. And actually come from the previous slide. Let me clear the screen, right? It's this. So that's why I wrote, this is its own variance. Okay, if you don't like, you can replace this by, this is sigma x bar squared. You can replace this by sigma if you don't like this. Is that okay, Ho Ying? I hope that's okay. Any further question? I guess that would be, let us define it, okay? This is the confidence level estimator, okay? Is based on the point estimate, okay? We add and subtract certain thing, and by central limit theorem, this is normal with mean mu, sigma square over n. And based on this idea, we can say if we want the mu x bar plus minus the me x bar plus the me, the probability of this is equal to 1 minus alpha, okay? Then what is this to me? This me will be this, okay? And the width of the interval, which means the top minus the bottom, will be 2 times this guy, okay? And sometimes this refer to UCL, upper confidence limit, and this is called lower confidence limit. Is it okay? Just nothing, but just give you a term. Okay? So there's nothing to understand. This is a term they give. Now, what we want here is the graph is the following. So what do we mean by 95% confidence here? Okay. Easier way to think is, suppose you have one sample, okay? The sample mean is this number, okay, normalized sample mean, right? And then you can give this confidence, right? Another sample you construct, it will do the same. Another sample you construct, we will do this, and you construct many of them, okay? And what confidence interval means that you construct, say, 100 of them, okay? You construct 100 CI, okay? 95% confidence means 95 of them, okay? The interval will include the mean. 95 of them will include mu, okay? And then 5 of them does not, okay? But remember, in the real world, we just do one common interval, right? We just do one, okay? So we cannot even say this, right? We can just say, that's why we're confidence. It's not probability, because once you draw, it's no longer probability, right? Once you draw, the sample is there, there's no more random variable, okay? But what we say is, suppose we repeat this many times, and 95% of them, you say alpha is 5%, right? 95% of them will include the mu, right? But we don't know actually include which 95, but we just only know 95 of them will include, but we don't know which 95, okay? So that's a little bit tricky thing, but that's the main tricky part in this confidence interval, okay? Interval estimator is not, we don't have easy interpretation of that. Is you have to go back to say, we repeat many of them, then 95% of them will meet it. Actually, same as unbiasedness is saying that, it's not saying that what we try to guess is exactly what we want, but we say, suppose we do many of them, the average of those will meet the target. So here again, the similar idea is like, we repeat many of them, 95% of them will include it. Okay. So if you don't have question, let's see the example that will give the idea. Okay. So now somehow we know the population standard deviation is 4. So sigma square is 16, right? So sigma is 4. And sample size is 64. And sample mean is 3. Okay. Now we want to construct a 95% confidence interval. Okay. Sample means 3. Okay, so we look at the Z table. What is this number? Right. So it's if you like try to show you, right, this, right, let's look at the Excel. So we want 0.95, okay, and 95%, remember here, can you see the Excel spreadsheet here? So we want this to be 95%, okay, or this is 0.95, okay? So we want the tail is either 0.025, okay? This is also 0.025, okay? Or this is 0.975, okay? So either you can find a negative value or you find a positive value, okay? So you can do the two things here, okay? Either you can use this or you can use this, okay? Norm standard inverse of this, okay? Actually, they're symmetric, so that's why regardless of what you use is 1.96. That's why I use in this slide. So is that clear what we are doing here? Is that okay? So let's go back. So now we know this is 1.96, right? And that's why you can put here, right? Because this is Z alpha over 2. We want sigma over root n, okay? Sigma is 4. See, okay? Root of, this is root n, 64 here, okay? Is 0.983, okay? So that means that if you try to guess what is the 95% confidence interval for the mean will be 3 plus minus 0.98, so it will be 2.02 or 3.98. Okay. So very quickly, I give you just because we start late, we just have give me 4 more minutes. So this one will be also very easy. Okay, let's see. Okay, and suppose we don't know the population variance. Okay, use S. Okay, and actually we know this, the sample mean we followed here, right? This what we learned last class is this over S over root n will be following a Tn minus 1. Okay, so do note that it's Tn minus 1. Okay, so that means that you have the same idea here. Okay, but the margin of error, right, will be Tn minus 1 alpha over 2 S over root n. Okay, so that is what we saw in the next slide. So this is what it is. Okay, you repeat the same thing, the proof is the same. We're not going to do it. Instead, we will go into give the example. Okay, this is a rather easy example. So this is the last slide. After this, we'll see you in the next, in first day. Okay, so sample mean is 20, sample size 20, sample mean is 3. Okay, sample standard deviation is 12. Okay, so I want to construct a 95% confidence interval for the mean. Okay, so we know it's 3, so it must be 3 plus minus certain thing. Okay, And so here, first, you need to look at this Tn minus 1 0.025, okay, which gives you this number, okay. Let me show you in the Excel, okay. So we have n is 20, okay. So again, you will give the same trick here, okay. But now it's no longer a norm, it will be t invert. You need to put degree of freedom, which is 19 and minus 1. Okay. It should be 19. Okay. So so this is 2.093. Okay. So I guess there's a typo. So it shouldn't be 15. Because now I have 20 here. So this should be T19.205 should be 2.093. So there's a typo here. So this is the same. So 2.093 times 12 over root 20. So what's the big number? So let's do it together. So this should be this times 12 over square root of 20. Okay, it's 5.65. Okay. Yeah, 15 is typo, yes. So it should be 8.6 to 2.6. Negative 2.6. So I hope you can correct it on your own side. This typo here. Okay. Okay. So let me correct the typo. Again, just make sure that you correct it. This is not 15. This should be 19. Okay. And this number is 2.093. Okay. This is 2.093. And this is 5.616. And this is 2.093. This is negative. Yeah, negative 2. So this is negative 5.616, negative 2.616. This is 8.616. Okay, so that should be the answer. Okay. So so that's the end of the day. So we will be finishing the very quickly very soon. So I think we are not. I think we're still probably on the schedule right now. I guess not in a rush. I guess it's we are fitting the schedule. Once you use inverse and not inverse. Thank you very much. I will say bye-bye first, and then before answering the question, say bye-bye, thank you. There's a question. Yeah, thank you very much. The question, what do you do inward? Yeah, say bye-bye. So don't worry, you can just leave. Say the question here people ask is when to use inward, when to use Excel, okay? If you give me the particular Z value, okay, the Excel function is the probability Z less than Z, okay? F of Z, okay, is this function, given the Z, given probability is norm standard this, okay? Which means that I give you, you give me the Z value, I give you the probability, okay? You go this way, from this to this is norm this, okay? And if you go the other way around, from the probability total here is norm standard inward. Is that okay? Convert to normal and not normal is not related to this formula. You just multiply the mean and just normalization, right? Just equal to Z. Inward is just you from probability to the Z value. It's inverse of this function. Actually, the opposite, right? You can easily see there are two different sides, so that's why they're inward. Is that okay?
It's okay.
Yeah, good. Jungsop, is it clear?
Professor Cole，
請講。
你可唔可以俾多次個 Excel 我哋睇？
哦，唔好意思啊。
唔該。
Is that okay?
OK 啦，唔該，拜拜。
Thank you. Bye-bye. Is there anything I can help? Just try to make sure that you don't have the problem with you when you go home. I don't know, when you stay at home, probably. You see, is there anything I can help? Hi. If no, I'm going to end the section because there's another one. Is it okay? If there's no further question, then I end the section. Thank you very much.